If a three-phase symmetrical fault occurred at point F of a 33 kV network connected with two sources, source 1 and source 2, then the fault current will be supplied by both sources. Notice that in spite of lower fault level at bus bar B, source 2 is supplying more fault current than source A. Also notice that for a fault at point F of line 2, line 1 is supplying fault current from substation A to substation B. But how to calculate this fault current distribution? In this video, we will discuss how to calculate fault current distribution in a 33 kV network synchronized with two grid sources. Before calculation, we will know details of the 33 kV network we are discussing about. This 33 kV network consists of two substations, substation A and substation B. They are connected by two parallel transmission lines which are 10 km long. Fault level of substation A is 8000 MVA, whereas fault level of substation B is 5000 MVA. Both substation A and substation B are connected with grid, and we will call this as source 1 and this grid as source 2. We will calculate fault current at point F and current distribution in different lines and source of this 33 kV network. Use per unit method, delta star conversion for network reduction, and then superposition theorem for solution of this problem. At first, we will find per unit impedance of transmission lines by using this formula, and we will consider base MVA of this network as 100 MVA. Actual impedance of transmission line 1 is 0.3 ohm per kilometer. So for a 10 kilometer line, actual impedance is 10 kilometer into 0.3. So we write 10 into 0.3 as actual impedance, and when it is multiplied with base MVA, that is 100 MVA, and divided by 33 kV square, then we will get per unit value. As the fault occurred 4 km away from substation B, so actual impedance of ZL2B is 4 km into 0.25 ohm per kilometer, and per unit impedance of ZL2B is 0.092 per unit. And as ZL2A section is 6 km long, so actual impedance of ZL2A is 6 km into 0.25 ohm per kilometer, and per unit impedance of ZL2A is 0.138 per unit. Now we will calculate source impedance of source 1 and source 2 by using this formula. Fault level of substation A busbar is 8000 MVA, which is supplied by source 1. So fault level of source 1 is 8000 MVA. So source impedance of source 1 is 0.0125 per unit, and fault level of bus B is 5000 MVA. So source impedance of source 2 is 0.02 per unit. To calculate further, we will redraw our network like this. Here ZS1, ZL1 and ZL2A are connected to same point, so we will consider that one node, and ZL1, ZS2 and ZL2B are connected to same point, so we will consider this as another node. And as ZL2A and ZL2B are connected to this point, so this is the fault node. We can reduce this network like this by using star delta transformation. We will calculate value of ZA, ZB and ZC by using these formulas. We can further reduce this network like this, as ZS1 and ZA are connected in series. So equivalent impedance of ZS1 plus ZA is 0.0875 per unit. Similarly, ZS2 and ZB are connected in series, so equivalent impedance of this part is 0.07 per unit. Now as these two parts are connected in parallel, So equivalent impedance of this part is 0.0388 per unit, and ZC, that means 0.025 per unit, is connected in series with this equivalent part. As these two parts are in series, so fault impedance up to fault point is 0.0638 per unit. So fault MVA at point F is 1567 MVA by using this formula, and fault current at point F is 27,416 amperes. So question 1 is discussed. Now we will discuss question 2, that is current distribution in different lines and source. We have already calculated fault current at point F, which is 27.4 kiloamperes, and this fault current will be supplied by source 1 and source 2. But what is the contribution of source 1 and what is the contribution of source 2? Now, as impedance of these two parallel paths are known, so fault current sharing of source 1 and source 2 can be calculated by using current dividing rules. So fault current sharing of source 1 is 12.18 kiloampere, and sharing of fault current by source 2 is 15.23 kiloampere. For a fault current of 27.41 kiloampere at point F, fault current sharing of source 1 is 12.18 kiloampere, and fault current sharing of source 2 is 15.23 kiloampere. But what is the current distribution through lines? That means through ZL1, ZL2A and ZL2B impedances. To know that, we will use superposition theorem, where we will use only one source at a time. At first, we will consider source 1 is connected where source 2 is disconnected from network. Now, we already know that fault current sharing of source 1 is 12,184 ampere. So, we write that here. We have already calculated per unit impedances of ZL1, ZL2A and ZL2B. Now, in this case, ZL1 and ZL2B are connected in series. That means ZL1 and ZL2B are in series connected, and this section is in parallel with L2A. So again, by using current dividing rules, we can find value of IL1 S1 and IL2 S1. Calculated value of IL1 S1 and IL2 S1 are fault current through line sections due to source 1, which are shaded and written by green ink. Now we will consider source 1 is disconnected and source 2 is connected, and we will calculate value of currents through line sections due to source 2, and we have already calculated that current sharing by source 2 for a fault at point F is 15.23 kiloampere. And in this case, ZL1 and ZL2A are connected in series, and this series part is in parallel with ZL2B, that means this section. So again, by using current dividing rule, we can easily calculate value of IL1S2 and IL2S2, which are fault current through line sections due to source 2, which are written by red ink in this diagram. Now, by superimposing source 1 and source 2, that means green and red current, we will get actual value of fault current with direction in this 33 kV network. Hope you understand this topic. For more video like this, stay tuned by subscribing this channel, and don't forget the bell icon for instant notification.